you want to try to figure out which is the best model for the data. Okay, so we're just going to use Bayes' rule. That's all we're going to do. So we've got this collection of models, say M1 through to M little m, and maybe have some kind of prior preference for each of these models. So that's probability on each of the MIs. And then if we've got a data set, script D, we want to just figure out the posterior probability of each of these models given that data. So that's proportional to the probability that each data set would be the data set generated by each model, the likelihood term, times by the prior, and this P of D is just the sum or the integral of the numerator of the models in this case, the sum of the i's of the models. Okay. So that's easy. This is our general expression. And to compute this likelihood term for the data given model, in general, we're going to have some parameters for each model, say theta I, and we're going to have to integrate each of these models over their respective parameters to get their probability of the data given model. So this term is often called here the marginal likelihood, or sometimes called the model likelihood. And I probably will use this term interchangeably. So that's it. Basically, there's nothing really more to Bayesian model selection than that in terms of the general theory. What's going to cause some problems, though, is carrying out these parameter integrals. These are going to be complicated to do in general. So, many models have many parameters. Carrying out integration in high dimensional spaces is difficult. This is really the bottleneck for carrying out this Bayesian model selection. But if we can do that, given then say two models, Mi and Mj, we could say which one do we prefer. If we wanted to do that, we could say, well, compute the posterior probability of model I compared to the posterior probability of model J, and that's then just given by this ratio of the two likelihoods called the Bayes factor times by the prior probability ratios. Okay. So the one thing to bear in mind a little bit is that if you compute this model probability, say Mi, and you get some number now, so it's 0.1 or something like that, this doesn't mean the sort of the posterior probability of that model sort of in an absolute sense. It's just relative to the set of models that you considered. Okay, so it's not something like somehow the best thing in the world. This is the best model in the world with probability 0.1. It doesn't mean that. It just means that according to the set of models that you have specified, this is the relative suitability of that particular model. Okay. So we've done something a little bit similar to this before, where we say, well, okay, let's have a coin, and the question is, there are two models. The coin is either biased or it's unbiased. Okay. So the coin is either fair or that's the first model, so it's biased in some way. And according to the probabilistic framework in mind, we have to make models. So what do we mean by a fair model? Well, I could assume that for a fair coin, the probability of it coming up heads is pretty close to 0.5. It might be there are some manufacturing defects which might mean there's this very small probability, but it might not be exactly 0.5, but it's close to that. That was what I could characterize as what I mean by fair coin. On the other hand, I might characterize a biased coin as, well, whatever it is, it's got a very low probability of being 0.5, probability of coming up heads. But there's some higher probability, might be biased, say, towards coming up tails or more likely to come up heads. That's, people say, well, I don't agree with that. That's not really what I would call bias, but that's fine. It's a broad church, the Bayesian one. It's really, it's up to you to argue your case about which models you prefer, but that's okay. You just have to, the only thing that we require is that you explicitly declare your interest and what you mean by your models, and then the rest will just crank the machinery and calculate the probabilities. Okay, so then what we're going to do, so that's our prior and our models, and we want to compute then posterior probability of the data the models given the data. So first of all, compute the model likelihood. In this case, if we've got theta as the parameters, we need to integrate or sum over the parameters. And here I'm going to sum over the parameters to start with, just to keep it simple. I'm going to assume that the only values of the parameters are between 0.1 through to 0.9. There are just a discrete set of parameters here. So that means that in this case, the model likelihood is given by this summation term. Then this is easy probability of theta given m. Well, that's given by the model prior. Okay, so this probably should be, see this in the fair case for each theta, you've got a probability. And you have to multiply that, the data term from the IID is just going to be, as we saw before, the number of heads of power theta times by minus the probability of tails, the number of tails in your observe. And that's going to be your likelihood, your model likelihood time. So we're going to get then this expression when carried out is this kind of slightly weird thing where you have to multiply all those things and you'll get that model likelihood time. Okay, we need to do that then for each of the settings, in this case there are two, for the model, either the fair or the biased one. So if we assume, say, that we don't care, have no preference for whether or not the coin is, say, fluoride biased or not biased, and this base factor is just given, so this posterior ratio is just given by this ratio here, because the priors are the same, so they cancel. So for example, if you saw 5 heads and 2 tails, then you compute that the probability of data getting model fair is this, its bias is that. If you compute the log the ratio here, you get about 1. So this is interesting, and it says that, okay, so you did observe more heads than tails in this case, but you don't really have much of an idea as to which is the preferable model. This ratio is very close to 1, so there's not a lot of data to really figure out which is really the most appropriate model. If we though go this to 50 heads and 20 tails, so the ratio of heads and tails is still the same, then this jumps down to 0.1, and we're getting less confident that the fair model is actually completely correct. Okay, so that's nice. So that's the general procedure, and we saw also that we can extend, say, this discrete parameter space to continuous ones, and the natural one to do with this bias, which is the new process is just to use the beta distribution. And categorical case for more than 2 states, we use the Dirichlet distribution, and everything is finally good and it's working out nicely. Okay, so we're going to lead up to those slightly more complicated things where we want to look at, say, fitting, say, models to data, like continuous variable models. Okay? But before we do that, I'm going to look at another case. Maybe I'm getting less enthusiastic about this example, but I'll go through it anyway. I think it's perhaps slightly missing the point. But let's look at a dice. Okay, so what we're going to do is you're going to have a total score of dice. So dice are these 6-sided things, are cubes, right? So you toss, I don't know, you toss them. Maybe you don't notice them, but they've got 1 to 6 on them, and then so if you say got say 2 dice, maybe somebody tells you, well, the sum of the score of the 2 dice is 12. Okay, so clearly it have to be 6 and 6. There's no other split there. But if they said actually the sum of the score is 4. Right, there are more possibilities. It could be 2 and a 2, or 1 and a 3. But actually, let's imagine now we're in a situation where somebody says, actually, I don't tell you how many dice were actually involved. I just tell you the total score. And you want to know something about the distribution of the number of dice that could have been involved in generating that total score. So that's the kind of inference process. So let's say the total score in the end will be 9. We want to know the distribution of the number of die or dice. I never know which. Is it die or dice? I think the English language is modifying around this point actually. I think at some point there's some confusion about whether. Would you prefer to call it die or dice?
Die is singular, isn't it?
Yeah, die is singular.
Die. Die is singular, dice is plural.
Yeah.
Oh, okay.
But no one really cares.
No. I'll probably say dice. Yeah. Okay, so we want to know the number. N is going to be the number of dice, and so T is the total score. So we want to know that. So given use base rule, that's proportional to this. And let's assume that I don't care a priori about the number of dice. I don't know that. I put a constant flat pi over the number of dice. And this likelihood term here, probability of T given N, well, let's say that S is the score of each of the individual dice. Okay? So to get this, I need to sum over that to get this probability. And then assume that the data are IID. So in other words, when you toss these things, that they don't affect each other. So this is given T given S times by P of S. And a priori, the pri on P of S1 through to Sm, that they're independent. So we have looked at this time here. And this P of T given S1 to Sm, well, that's easy. So if you tell me what the dice score are individually, you just sum them up. So that's just a delta function. So in other words, you can write that as an indicator. It just says, well, the total score is equal to T. Right. Then we get this term here with the probability of each of the individual scores. So if these things are uniform, so the probability of generating a 1 or 2, 3, 4, 5, 6 is each 1 over 6, okay, then that would be specified, and then we just need to work out this. So in other words, we need to go through all those probability combinations, multiply them with these probabilities 1 over 6, and we need to just get those ones which actually give a total score of 9. And that will be the likelihood. And then we can repeat that for different numbers of these dice. Okay. So for example, if you do this with, this is T now, the total score going on here. There's a number of dice going down here. So if we start with one dice, this is the probability of generating the various scores 1 through to 30 for that dice. So we can generate these scores, okay, with the uniform probability. So the probability of generating a T plus 9 is 0. For 2, the probability of generating T plus 9 is higher, it's non-zero. And to increase, the probability of generating T plus 9 actually starts to decrease a little bit. Because the model in some sense is getting more, there are more states you can access. Because the total number of, the probability mass is to sum to 1 over all the states you can access, then the probability typically then of generating any individual state is typically going to start decreasing as we get more and more states. So you could think about this as, well, let's say then you say, well, actually I observe 9, that's the given thing. And we could look at this and say, well, posterior probability then of the number of die which are involved is going to go something like that. So it's going to be 0, 1, and then it's 2 and 3 are quite high, and it's going to start dropping down. So yeah, you could sort of talk about this as some kind of complexity thing. So yeah, I'm slightly less enthusiastic about this description. So I'm going to move on to something else. But you see a little bit, one of the points is that as the model gets more complex, there are more states you can access, and in some sense, that can, because you have a uniform probability over the states which you can access, that means that any individual state typically will have a low probability of access. Okay, so I think this one is a little bit more interesting example. So in the exercises, there is just to prick your ears up for those of you who like finance and stuff like that. So there's an example about a hedge fund in one of the chapters where you're going to try to figure out what are the relevant factors for predicting the stock market. So believe it or not, these guys actually do this. So they do something like this. They say, well, the price of the stock which I'll call, say, y, is equal to some kind of linear combination of some kind of factors of the stock. So, for example, you guys probably, some of you know more about this than I do, but this might be some kind of indicator of the stock market, like say, I don't know, maybe this is something to do with the healthiness of the company, or maybe it's something to do with the momentum or the trend of the stock price over the last few days, or some kind of economic factor, like, you know, what are interest rates, or, you know, or anything you like, really. You can just plug them in, or it could even be the prediction of an analyst. Maybe you're paying these guys a lot of money to give you what they think is their prediction of the stock price tomorrow. So based upon all of these observable factors, these x's, y0 or y might be your prediction of the stock price of the stock tomorrow. Okay, so you could go back historically and say, well, that's cool. I've got this historical set of these x's, and I've got the corresponding next day price, and then I want to find these weights, you know, which somehow best minimize or give me the best prediction, or would make me the most accurate next day prediction model. So you could say, well, all kinds of things you could do least squares, that's fine, but typically what's going to happen is the more of these things you include, in some sense, you know, the lower the least square error is going to be. You're just going to get lower and lower, and then you're going to overfit, right? So this is not really what you want to do. You really want to find, in some sense, the subset of these factors, which is really the smallest one, which gives you, in some sense, a reasonable prediction. Because then maybe you've really captured the real signal, and you're not overfitting, you're not fitting the noise in the data. Okay, so maybe a better example would be, let's say you have data points like this, and you know you need to fit, say, something to this data. Or you could say, well, I could fit, say, a straight line. That could be a reasonable thing to do. Of course, it's not perfect because you've got some residual errors here, so that's not bad. But somebody else would say, well, look, I've got a really fancy model. It's very complicated. In fact, you can fit all of the data points. It goes through them. So we have zero error. Let's say the least square fit. The difference between the actual model and the data points is essentially really small, so it's essentially zero. So that's kind of a better thing, right? But then you come along with your new data point, and you ask, what is the value of this point here, some x here, and you want to find the corresponding y. Well, your complicated model is sort of varying wildly in order to fit this very complicated, noisy data. So you really don't have much of a clue, maybe what the real answer could be there. It's just overfitting the data. You've not captured maybe the real underlying trend of the data, the smooth, non-noisy part of the data. This is a little bit, kind of difficult to discuss, but in some sense, typically what we're looking for is lower dimensional, simpler descriptions of the data. We want to find descriptions of data which are low, simple things, low dimensional, simple descriptions, such that they fit the data well with a small number of parameters. There's a kind of a trade-off there. We don't care about perfect fitting. Similar with parts and estimators, we don't care about, fitting the data completely. We want we're happy to give up some perfection in terms of model accuracy to get a simpler model. And that's really what we're looking for in the model. Okay. So this is a similar thing with the stock market. So what they do there is, the question is, maybe this analyst that you're paying mega bucks for to predict what's going to happen with the stock price of some share tomorrow, actually he's hopeless. It's just not better than just looking at the interest rates or something like that. Maybe that's a useful thing to do prediction. So ideally, you'd like to get rid of this guy. You don't have to pay him anymore. Right? It's good. So then the question is, how to do that? How to identify which of these factors is relevant? that's one thing. You can address that one way using what I'm going to tell you now, and using this Bayesian model selection method. Okay, so let's look at a model of this form. So this is a linear model. We're going to look at a specific one where these, so this form, say y0 is some constant plus some cosine terms. Okay, so this is a kind of discrete Fourier representation. So it doesn't really matter too much, but essentially these things are, you know about cosines, right? They're just oscillating functions through x. So we've got the different periods of the oscillation here. So the question is, we're going to take these sets of functions. That's going to be some particular frequency. Another one, say, double the frequency, triple the frequency, etc. And we're going to take a combination, a weighted combination of these functions and try to reconstruct the signal using this. Okay, so you may say that's a really weird thing to do, but it's a very common thing to do actually in science, right? To decompose a signal into its Fourier components. It's a very characteristic thing we like to do. So the question is, what are the Fourier frequency, what are the Fourier components that you would need here? So what I could do is I can first of all write this linear combination in a little bit of a more descriptive way. So I can write y0 is w scalar product of this weight with, say, some feature function of the input x. In this case, this feature function is just a vector function of x, which is given by this. Okay, for a up to k weights in this decomposition. So in general, you can put any phi that you like here. It doesn't matter. And we're going to, for this particular example, use this setting here. And then we're going to assume that the data we actually have are noisy instances of this model. Okay, so it's going to be the real clean signal for some particular x, plus some noise coming from a Gaussian, the zero mean and the variance given by sigma squared. And the question then is, for a given data set, how many of these components should we use? Well, we can use Bayes' rule. So we want to know what's the probability of k given d. So that's probability d given k. Okay. So again, if I just set k to constant, I don't care about that term too much. But the probability of d given k is the probability of all these y's given x and k. Okay, so I'm just going to, well, in principle, I'm going to assume that I would have to have a probability of the x as well, but my model will not make there will be no parameters about generating x in this case, so I don't care about really modeling x, so I can essentially really assume this term here is a constant. Okay, so in other words, I'm going to, so the likelihood for the data in principle is a model for the observations y and the inputs x. But my model itself will be of the form phi y given x and theta times by phi of x. I'm not going to put any parameters on x. So I'm just going to say that x is always fixed. Okay, so I'm not going to care about that. So that's going to be some constant term which I can essentially neglect. Maybe we can come back to this point if it's unclear later. So this likelihood term here, this phi of y given x and k, well, this is like we saw before. We have to sum now over the parameters, or in this case, integrate if we have continuous parameters. So it's going to be integral of the prior times by, if the data is IRD, this data term here. Is this clear? Get the comrade into everybody else? It should be reasonably clear. So if I give you these data points here, what is this? This is just, we could call this P of y given x and k. So we don't know what it is, but we do know what it is. If I told you what the w was, the parameters were, you would be able to write this down. So you just in general say, well, this is, well, let's see, I integrate over W, y1 to y n, give x1 to xn. That's just a marginal likelihood. So this is equal to the integral over py1 to yn given w at x1 to xn as bipositive w at x1 to xn. Because we're assuming the data is independently generated, this is the integral, the product over each data point over y n given x n and w times by this term here. So we're going to assume that the prior is simply independent of x. So that's our expression. I've got to write the k dependency here. Alright, so we need to work this out, actually. So we've got everything now. What is yn given xn wk? Well, we said that y is generated from a Gaussian with a mean given by w transpose times by phi. So this means that the first term, so the term yn given xn wk. So this is supposed to be Gaussian with the mean given by the clean thing, which is just basically w transposed phi of xn. Is that a variance of sigma squared? Okay, where phi is a k-dimensional, it's our kth dimensional feature vector. Okay, w is a k-dimensional vector. So I can do all of that, and I can write that down here. I have to now choose a prior distribution over w. So this is a little bit of a tricky thing to do. So what w's would you like to have? So we need to choose a w in a k-dimensional, it's a distribution of a k-dimensional continuous w. Okay, so there are not a lot of distributions that we can choose, unfortunately, which will make integrals tractable. But we could also say, typically, at least maybe for this cosine case, I don't expect to have massively large values for these weights. Maybe I would expect most of these weights to be kind of around order 1, something like that. Maybe plus or minus 1. So I kind of want to constrain this thing to be reasonably within kind of roughly a unit sphere, something like that. So I could choose a prior on W to say, well, it's just a Gaussian distribution, say with 0 mean and unit covariance matrix. Maybe scaled by some vector. Okay, so it's just, that's a choice. And this inverse covariance is also called this variance is called the precision as well. The good thing about this choice actually is that this term now, so this, you take this product here over n, what you get a sum in the numerator over n. But that means that as a function of w, this is actually just a squared quadratic form here. Okay, so that's good, right? Because we can integrate. It looks like a Gaussian w. So if I choose a Gaussian prior in w, I'll just have an e to the something quadratic in w from the prior, got an e to the something quadratic in w from the likelihood term, which means I can kind of combine terms together. I'll end up with an e to the quadratic something in w. So that means I know actually the posterior distribution is Gaussian. So that means things are going to be easy. So one way to do this is to say, well, let's write this exponent down. This is sort of the the naive way to do it, and let's identify what is the quadratic form there in W. So the log of this posterior distribution, or the log of this term here multiplied by that term, the log of this exponential of this expression here, where I'm just collecting the W dependent terms. So the let's do this. Have you guys done Gaussian integration actually? No, you haven't done this. Okay. Let's just park this here for 1 sec and do an interlude. Divertimento. Okay, it's going to take 5 to 10 minutes, but hopefully it'll be useful. So Gaussians, you know about Gaussians, right? So what is a Gaussian? A Gaussian is, in one dimension, the most famous distribution of them all. P of x is x with the mean variance sigma squared is 1 over 2 pi sigma squared e to the x minus mu over 2 sigma squared. This is the Gaussian distribution, and it's got mu, it's got standard deviation sigma. This is the thing you get burnt into your brain after a while. So this is like there are some fundamental reasons in science why this is the most important distribution in science. And, that reason is the central limit theorem, which I'm not going to go into, but it essentially says that typically in the way the world works, things are often linear, so that what you observe is a summation of many things. Okay, that's the way physics works. It's just a linear superposition of waves and all kinds of stuff like that. So because you have kind of noisy measurement devices, typically what's going to happen is that you are trying to measure sums of things. These sums typically tend to be Gaussian distributed. That's what the central limit theorem says. Whatever the underlying distribution of objects is, the summation of them will be Gaussian distributed. And that's why this is the most important distribution in science. Okay, now, Gauss was a clever chap. Right? How the heck? So he figured out that this thing here sums integrates to 1. Right? So this is very interesting. So what this means, we have to have the integral of this over all space equals 1. That's the definition of a probability distribution. So what that means is that Gauss figured out that the integral of e to the x minus mu squared over 2 sigma squared is over 1. It's equal to 1. In other words, he figured out that this is equal to 2 pi sigma squared over the real line. And you might think, oh, that's okay, it's interesting. No, you go back to school and you think, well, what did I learn about in school, to do integration? You learn various tricks, right? Like substitution of variables, or partial integration. Right? These are some of our tricks that we use to integrate stuff. You can play around with those till the cows come home, and you will not figure out how to integrate this thing. So it's tricky. It's kind of it's quite remarkable that the most important distribution in science, unfortunately, is beyond the school level calculus. It's not really actually, but it doesn't fit in the standard tricks that we learn about. So I'm sure some of you have seen this before. I mean, there are different ways to actually calculate this integral, but it's interesting, as part of your general education to know about this. So, who knows about how to do this? One or two.
Sure.
So you got to buy the bullet at some point. So we may as well do it now. Okay. So the classic trick to do this is we're going to first of all look at a slightly simpler problem. Let's say that we set the mean to 0 and sigma to 1. Okay. So we're interested in the integral of e to the minus x squared over 2 dx. So what we could do is we could call this, say, this integral I. So this means that I squared is equal to the integral, that's an easy x squared over 2 dx. Okay. Pointless, apparently. But it's this x is just an integration variable, so I can call it whatever I like. So I'm going to call it y here. Well, this is, the mathematicians in the audience will sort of bury their heads in their hands now, but I'm going to say I can also write this as, I can interchange the integration and these products to say, well, this integral from minus infinity to infinity, that's infinity, e to the minus x squared plus y squared over 2 dx dy. Reasonable. All right. So what this means, I have to integrate over all real space. Okay. So what's interesting about this now is you can use a coordinate transformation. You could say I'll switch to polar coordinates. So in that case, you might say x equal to r cosine theta, y is equal to r sine theta. Right. So that means that this integral now, I squared, so we have to integrate over all of the real space. So that means that the r is going from 0 to infinity. You've got this radius term here, r, you've got theta here. So r is going from 0 to infinity, and theta is going to go from 0 to 2 pi. That will then be the real space integral. So x squared plus y squared is equal to r squared. Because x squared plus y squared is equal to r squared times pi cos squared plus sine squared, and this is equal to 1. Right? So we get e to the minus r squared over 2. Now we've got to transform this dx dy to the equivalent sort of volume element or area in the polar coordinate thing. So I don't know if you remember this, but it's this Jacobian thing that you have to do. And if you work that out, this dx dy gets transformed to r dr d theta. So you get this r dr d theta. This is the Jacobian term from coordinate transformation. Okay, so let's carry out the integral over theta. So this bit here doesn't depend upon theta, so that just gives us a 2 pi times by the integral from 0 to infinity of eta minus r squared over 2 times by r dr. And this is good actually, because this is easy to integrate, because we can just differentiate eta minus r squared, we'll pull down first of all the derivative of r squared, which is minus r, okay, times by whatever we had before. So this is good. So the integral of that is just minus eta minus r squared over 2. So we've got eta minus r squared over 2 minus sign 0 infinity. So e to the minus infinity is 0, and e to the 0 is 1. So we get 0 minus 1. So we get minus cancel out, so we get 2 pi. So that's I squared, so that's cool. So we so that means the integral of this 2 dx is equal to the square root of 2 pi. So this is the classic. I'd actually, to be honest, I don't know how Gauss figured this out. It's remarkable, really. But there you go. And there are other, there are more sophisticated ways of doing it, of course. This is maybe one of the nicest ways to do it. So I think every self-respecting scientist, should kind of have this bag of tricks, know about this. It's kind of, it is important to know about that. Okay, so this means you can, if you want to figure out this integral, this is easy because it's just a variable substitution. So we could say, if we call, say, the classic thing to do is say z equal to x minus mu over sigma, then this is equal to the integral. So x goes from minus infinity to infinity, but that's the same as z. If x goes from minus infinity to infinity, then z will also go from minus infinity to infinity. So that's the integral from minus infinity to infinity. This term here is e to the minus z squared over 2. That substitution. Dx is equal to sigma times by dz. Sorry, dx is sigma times by dz. And we just figured out that this thing here is equal to the square root of 2 pi. So we know that this is actually equal to then the square root of 2 pi sigma squared. We supplementing this way with the sigma squared there. So that's it. So that's the way to show the normalization constant of the Gaussian distribution. So that's all fine, but actually what we're really interested in is the extension to the multivariate Gaussian case. Okay. So I want to know how to define Gaussians in more than one dimension. The way it's defined is that a multivariate Gaussian, in general, you define it to be p of x, you will e to the minus to x minus mu, I suppose, sigma to the minus 1, x minus mu, 2 pi sigma. Okay, this is the classical, this is the definition of the multivariate Gaussian. So some people write this in a really ugly way, actually, which I don't like. Some people like to write this term as 2 pi to the n over 2 sigma to the. It's the same thing. It's ugly, because you need to write down what the dimension is there. This is a dimension-independent expression. So it's nicer. The determinant, if you have a scalar pre-multiplier of the matrix, then the determinant just gets multiplied by the power of that scalar. So this is, I don't know why people insist on writing that down. Actually, I don't like it at all. It's the same thing, but it's much nicer to write down. Okay, so this thing actually is the most obvious thing to do is to define a Gaussian where you have a Gaussian in each dimension. So we could say maybe define x1 and x2. Maybe have a mean here. And we could say, well, maybe we define a Gaussian distribution. I'll draw this very well. If you were to look at, say, the x1 dimension alone, you end up with a Gaussian distribution over the distribution of x1. If you look at x2 alone, you have a Gaussian distribution in x2. And they're independent. Okay, so that's the, if they're independent, you get this spherical structure, this distribution. This acts as a line kind of effect. So this is looking, if you made the substitution that z is equal to sigma to the minus a half x minus mu. Okay. Then this distribution here looks like e to the minus z transpose z over okay, so in other words, what I'm trying to say here is that this is z1 squared plus z2 squared, an exponent, which is the product of the individual z's. So in other words, under this linear coordinate transformation, it's equivalent to having independent variables. So in other words, in general, a Gaussian distribution, is just an independent variable which has been transformed to get dependencies. It's been linearly transformed. So there's correlations and dependencies you observe here are just because of the transformation of an underlying linearly distributed, independently distributed Gaussian variables. So just for interest, what we need to show is that the integral of this thing here in the numerator is actually equal to this thing down here. So we're gonna do a similar trick just to show you from before. So we're gonna make this first of all this transformation of variables right here. So the integral of e to minus x transpose sigma minus 1 x minus mu over 2 is equal to the integral of this thing now. So we're now going to have we had a dx here. So we need to know what the dz is, right? So the dz, so the Jacobian of this thing will be just the determinant of this thing to the half times by dx. This is the Jacobian for this linear transformation. So the Jacobian is just the determinant of the partial matrix, the partial derivative matrix. So in other words, dx is equal to sigma to the half dz. So we need sigma to the half det dz. So that cancels with that. So we're left with, is that right? Yes. So let's go on here. So that's the wrong way around. Yeah, sorry, this is not there.
Yeah.
I'm just computing the integral. So this is the so det sigma to the half times by this thing, right? But this is just the integral e to the minus z1 squared plus z2 squared then n squared to the z1 to z2 to zn. which is then sigma to the half integral, which is the product of the integrals. And each one of these we just crude is equal to the square root of 2 pi. So it's equal to 2 pi 2 pi to the power n over 2. Number of the variables. Okay. All right, so that's how to prove that this is the correct normalization. Okay. Good. So in general, if you have expressions of the form, the integral of a kind of a quadratic function here, we can easily carry them out just by using this kind of trick. Okay? So what we're going to do is we're going to now go back to here, and we say, well, we need to carry out an integral here of this quadratic form. Okay, so what I'm going to do is I'm going to collect, first of all of the terms in W. I'm going to write a quadratic form in W. So I'll just sketch how this works, and maybe I'll not go through all of the derivation. So what have we got? So the first term is a Gaussian in W. It's P of W given K. It's a Gaussian term. So e to the minus W transpose it's zero mean Gaussian. W 1 over 2. There's an alpha term here for the inverse variance. So we have a 2 pi 1 over alpha the d, what do we call it? W, K, sorry, over 2. That's the Gaussian term from the prior P of W given K. And then in this likely term, we have e to the minus the sum of the data points. We have yn minus w transpose phi. I'm going to write phi n actually. So phi n is going to be phi of x n. Just clarification. Squared. It's going to be one of these denominators, normalization terms as well. So 2 pi sigma squared, and we're going to have an n over 2 of them. This is one per data point. Good. So we need to integrate this thing over W. That's what we need to do. So this looks, you might think at first, case, this looks really hard, but actually, when you get more, you love it, right? You think, oh, it's easy to do. It's just a Gaussian, actually. I mean, I'm going to do it the long way around, but normally we don't do this. We just jump straight to the answer. But at one point in your life, you have to go through this painful process. So the naive way to do this is to first of all re-express this as a function, a quadratic function of W. So what we're going to do is we're going to identify, we're going to say this is actually equal to some constant, which we'll figure out, as the integral of e to the, say, minus a half W transpose, say, AW, plus W transpose B. Where A and B are to be figured out. Right. It's clear that it's of that form because, what's A going to be? Well, A is going to be there's a W transpose W term here. So A is equal to alpha times by the density matrix. Right. The W terms here are going to come from, it's going to be W transpose phi n, then it's going to be phi n transpose W on the term here. So that means that A is going to be simply alpha plus 1 over sigma squared, sum over n by n transposed. Okay, that's coming from there. And then I'm going to have, there's no linear term here for w. There's a linear term here for w. So the b is going to be simply coming from the linear term. So we're going to have a, what is the linear coefficient of w? Well, it's minus the 2 cancels. So we should get something like 1 over 2, 1 over sigma squared, yn, something like that. Might be a factor of half now. And c is equal to whatever is left, which is not a function of w. So it's going to be this combined with that, combined with this term. Okay, so we know what a, b, and c are. These are all given. Functions of the data. Now you just have to evaluate now this integral over w for some given known matrix A, known vector B, and some just known coefficient C. So this is the only thing that we need to know now, how to figure out an integral like that. So it's not difficult because this is looking very much like a multidimensional Gaussian. Okay, so what we do is go back to school and we complete the square on this thing. So we say, what is the integral of e to the minus a half w transpose a w minus w transpose b? Well, I can write this, I can complete the square on this term. So I can write this as e to the minus w minus a to the minus 1b a to the minus a to the minus b. So if I multiply this out, what do I get? I get w transpose a w term here. W transpose a inverse, they cancel, b. So I get 2 w transpose b terms, which is what I want, and I get only one of them because there's a half there. But I'm going to get an additional term which I don't want, which is I'm going to get b transpose a to the minus 1 a to the minus 1, so I'm going to get b. So I'm going to get an additional plus, sorry, minus, because there's 3 minuses, b transpose a to the minus 1 b term, which I don't want in this expression here. So that means I have to add it on. So I'm going to have to add on, got the signs right, b transpose a to the minus 1 b. Okay. Good. So this is great because this is just simply e to the b transpose b transpose. That doesn't depend upon w. But this is now a Gaussian. If I call this thing here mu, and I call this thing here sigma to the minus 1, I've got a Gaussian. So this is just the integral of a Gaussian, which is just 2 pi times by the determinant of the Gaussian square root. So it's the 2 pi det sigma to the minus det of sigma. The sigma is a to the minus 1, so it's 2 pi det a to the minus 1 to the power of half. Okay. So that's the integral expression. So now what we need to do then, just for simplicity, I take the log of this thing. Just to write down the, just so the log likelihood. So if I write down the log, this is the answer. So I just jump to the answer there. It's good to know about this stuff actually. It's very useful. And that's it. So now this is great because we've got the likelihood, right? Explicit is a function of data. We've got the prior, which says we don't care about the number of components. And we're done. We've just used this now in the Bayes field. So here's my data points. This is some data generated from some model, which is of this this particular case. These phi's are coming from this Fourier stuff. And I want to figure out, how many Fourier components were there which were underlying this signal. And I think I'm going to assume that I know the noise settings here, just for simplicity. Okay? And in fact, I generated this data with 5 Fourier components, so k is 5, so some fundamental frequency up to the 5th harmonic. And then we run these things, we take this data, we just plug it into that expression there for the log of the data, and we exponentiate it. We then just do that for each of the k-dimensional k moles that we have. And then we compute the posterior just by normalization. And according to that, model number 5 is by far the most probable number of components that we could have. But this may seem, that the really interesting thing here is that you don't get 10. So if you had 10, of these, the 10th model is more complex than the 5th model. It's exactly the same, but it's got an additional set of components in there. So the 10th model is more powerful. It could express the data better than your 5th model. You could have a higher likelihood for that particular data set given a particular parameter setting. However, a posteriori is not the most preferred model. It's too complex. It's better to have a 5th dimensional model. And then with that 5th dimensional model, I can then reconstruct this. Okay, if it's really, let's say it's 5-dimensional, I can figure out what is the most likely clean data points to have given rise to those noisy observations for a 5-dimensional model, and it's given by this. This is the reconstruction then of the data for a 5-dimensional model. So that noisy signal here has now been reconstructed and cleaned up, and that's the dots are actually the real data before they got added with Gaussian noise, and the red one is the cleaned up data. So we were very, very close to the original model. So you can use this, for example, in all kinds of situations. People use these kind of things in audio reconstruction. So if you've got a recording which has got clicks in it and noise in the data, then this music is already there's a lot of frequencies in there, so you can basically use this thing to clean up the data, get rid of all of the noise in the recording. That's the thing that people do. There are all kinds of things you can do with this now. You could also use it for finance to try to find which are the important factors underlying your data. Yeah, all kinds of stuff like that. I think that's enough. Okay, so next time we're going to talk about how to approximate this thing in high dimensions.